point.
Great.
Very Korean.
10% now.
So stability is depending on current, but as well you will have different curves. Yeah, for example, melting, refining, yeah, or melting without reactor, melting with reactor. Yeah, so I start again a new one. Current. So this is typically melting. No reactor. Melting with reactor. And then refining. Yeah? When we talk about ECS, it could be very important to remember this information.
If we will consider only refining stages, it is a letter furnace. Same.
Yeah. Response time is
Late time.
so now you know exactly what is K. Yeah? This is this formula expressed by this one here. And when we have calculated here, we can calculate the XOP, which is here. Yeah? Again, you see this is a matrix calculation. Yeah?
저런 게 있구나, 함수야.
You see, everywhere you will have the same formula, because this is a matrix. Eh? No problem with the matrix? Yeah?
I have no experience to use the matrix in Excel.
You're not used? You're not used to use matrix?
Matrix in Excel.
You don't know?
Yeah, I don't know how to use it in Excel.
Oh, very easy. Oh, wait. Oh, I removed. Huh? You see, there is nothing. So this column is equal to this column time a constant. Time it was the X short circuit. Yeah. So then I press.
It's so easy.
No. Then I press majuscule, I, and control, and then enter. Ding.
Control
Control I.
high?
Oh, uppercase.
Uppercase,
Control.
caps, yeah.
Yeah, control uppercase.
Control caps and uppercase, okay. Really good. I know. This.
Wait, shift. 좋아, 좋아. No. You have to select all this.
일단 내서
All this. Yes. Equal.
맞죠?
This one.
전 관계에서 전문 아니에요.
Time 2, for example.
다행이신 거예요.
Control uppercase, enter. Done.
Okay. Very good. Easy.
Yeah. And it's very efficient for complex calculation.
Yeah.
And it saves calculation time. Because Excel is running faster with the matrix calculation.
Yeah. Thank you. So we use the one function and we drag. 컨트롤 시프트 엔터를 치면 좌우에 이렇게 딱 붙네. 그 블랙켓이. 그러면 이제 매트릭스 계산 바로 해줘. 우리 뭐 한개 곱할 때 한율 이런 거 변환할 때 저런 거 딱 쓰면 되겠네.
Okay, so having the impedance, we can calculate the out voltage. It's a big formula. Okay, so in order, the first part here, yeah, is to avoid to have stupid stuff. So the real out voltage calculation start here. Yeah. Because you see, I have a root, a square root of something with a negative value. So if this part is higher than this one, you get an error message. Error
message.
Yeah. So this is to avoid the error message, especially for the low current. Okay, I could start the calculation with 10 kilowatts, but so the out voltage is not this one, is at least this one. Yeah. So, but I do it in several steps. First of all, I calculate the square root. So in fact, it's the impedance. It's just an impedance calculation. Yeah. So this is the tap voltage square minus the impedance plus X meant. This is the impedance calculated previously. Here, yeah. Furnace impedance. Okay. Because this is in million, so I have to put in the same value. Square the current. Yeah. So this is the impedance term, and this is your resistance term. Yeah. Then from this, I just take the, just to avoid this is a negative value or stupid stuff, and then I take the square root. Yeah. Because here you see the impedance is done with the phase voltage. Yeah. So I want to have the earth to phase voltage here for the arc. So finally, the arc voltage is right here. Then the power factor. So this is this phase voltage plus the resistance plus resistance and a current divided by the tap voltage. Yeah. Again, it's easy to understand on the diagram. The cosinus phi is given by this ratio. This one, this length divided by this length. Yeah? So this is the arc voltage plus resistance and current divided by the tap voltage. Okay? Then, when I know the cosinus phi, I can calculate the active power. Yeah? The active power is the voltage times the current times the cosinus phi. Yeah? Then we come to the, this is difficult for you to understand. Yeah? This is the radiation index.
R means radiation index.
Yeah? RE. You know what is the radiation index? No. Okay.
Radiation index.
In the old time where there were no water-cooled panel, no foaming slag, that means they were only refractory. There were a lot of refractory wear. And people didn't know how to estimate how fast the refractory wear was going on. And there were a genius guy called Ben Bowman.
Genius guy.
So, remember this name? Who made study? In fact, he made a statistical study comparing several furnaces and using different voltage and different currents. And he established that the refractory index, that means the speed which with the refractory was worn out, was depending on the voltage, on the current, and on the distance between the arc and the refractory. The distance. This is the distance. Yeah. So he established a magic formula. So the radiation is proportional to the square of the arc voltage times the current divided by the distance square. Which means if you extend the distance between the arc and the wall, then you decrease the radiation. I mean, this is easy, yeah? So this is comparable to, let's say, a heat flux. Yeah. And this is rather easy to understand why we have arc voltage square, because it's more or less proportional to the active power times the arc voltage. Yeah? Almost. Power, of course, if you have more power, you have more radiation.
Mm.
But why do you have also more influence from the arc? Because if you increase the arc voltage, you increase the arc length.
Yeah.
And if you increase the arc length, you increase the surface where the arc, the solid angle, the solid angle where the arc is flaring. Yeah. And the distance is defined by furnace diameter minus PCD minus of electrode diameter. Yeah. Because you consider that if this is the electrode, this is the middle, and the arc is pushed away here, about here. So it just remove this part. Yeah.
This is electrode.
Yeah. Now we have everything.
D를 20도 결정하냐? D는 저렇게 하는데 그 전구로 직경하고 PCD 구하는 거를 알아야지 우리가 나오는 거지.
And we express this arc resistance in kilowatt volt per square centimeter.
전구 사이즈는 PCD만 구하면 D가 나오고
중국 사이즈가 나오는 것을 PCB도 작으면 작을수록 좋다면서 요즘.
그렇지.
나중에
전구 사이즈를 가만히 구하면 이게 지금 이거 엮이는 거야. 직경이나 D하고 파이가 같은 거야.
네? PCB. 아, 맞다.
2 곱하기 1이잖아.
아, 엮여있네.
그럼 1인데 그 D는
Per square centimeter.
What is the unit?
Yeah. This is the unit.
킬로와트 볼트?
네. 그
What
영향을
are,
미치는
what
D가
are the average values we consider for, let's say, furnace building? For melting phase, there is almost no limit. Yeah. Melting
시험적으로
up to 300, no problem, up to 300. Yeah.
What do you mean melting to up to 700?
인덱스 레디에이션
아, up to.
Yeah. Nowadays, considering the foaming slag index, we were limiting this time this refractory index to, let's say, 100. But we have seen that with the foaming slag, we can multiply by 3 as well.
100이 뭐야?
슬랩.
With the foaming slag, we can take this. It was limited to 100 in the past without foaming slag. With foaming slag, we can go to 300 as well.
You mean that heat flux from surface base?
What?
Radiation from base?
No.
From arc?
From arc. Yeah. For ladle furnace, it's limited to 50. Yeah. 50 is already a high value. This is the upper limit. Yeah. If we can go lower, it's better.
I have one question. Just wait. When we define the diameter of the EAF. The EAF diameter is have to be bigger than the 2 times of D. What is different EAF and D? EAF diameter and D, what is different?
This formula, because you have the furnace, then the electrodes are here. This is the PCD. So this is the furnace diameter. And this is the distance.
D.
So you have to take D minus PCD, minus, because the arc is here, minus 2/3 of the electrode diameter. Huh?
저는 어느 거든 한 개만 구하면 되네.
A가 저게 다이아미터라고?
예, EAF 다이아미터.
반지름이네?
반지름이네.
아니 2분의 1로 해보니까 다이아미터에 2분의 1 하니까 반지름으로 다 들어가요.
PCD
A가 EAF.
다이아미터.
A is not diameter is
Huh? A?
yes.
Where you see A?
You the one you told me the EAF diameter.
Yeah. EAF diameter minus PCD diameter minus 2/3 of the electrode
So
diameter.
so what's the EAF diameter from?
There's no problem of EAF diameter.
Is it 8 times 2.
8.
You mentioned the A.
A,
A.
it's age. Yeah,
No, this is D. D. You see? This is D.
That is actually not D.
저게 EAF.
그렇게 하는데 그래요?
저게 지금
아,
들어가는 게 I have
아,
this line and I write on this line D. Eh? D. Big D, small d.
Isn't it not R?
This is big D, this is small d. No, this is small d.
Isn't it not R?
Yeah, this is maybe radius of EAF.
This is
This is
okay. This is the radius, yeah. Okay, this is D. And this is PCD.
똑같은 2분의 5짜리.
이분을 넣어놨으니까 그렇죠? 제가 옆에 you're right. You are good mechanical. Because my hand didn't follow my brain, yeah. So
정확히 기하학적으로 D가 딱 그대로 정의되는 저렇게 맞잖아요.
그러면 저 스몰 D가 딱 되도록 전기로 사이즈를 정해주는 건가? 전기로 사이즈를 먼저 정해야지.
뭐래 스몰 D가 뭐래야죠? 일단은
그렇죠. 이게 레디에이션 인덱스가
아니 하는데 전기로 사이즈를 먼저 구해.
그렇죠.
저거를 고려를 안 하는 것 같단 말이야. 지금 이제 저렇게 D를 구하는 걸 보면.
그러니까 스몰 D는 앞에 게 다 뒤에 게 다 구해졌다는 전자에서 구해진다는 거죠.
그러니까 전기로 사이즈를 어떻게 구하는지가.
그게 있다.
How to calculate the diameter of the EAF? It's depending on volume of scrap or only. And we make a diameter and we define the small d. The EAF diameter is only scrap
and top weight related.
top weight and
Top weight.
scrap weight. 그럼 우리가 생각보다 우리 쉽네. 그지?
그리고 저게 뭐 레디에이션 인덱스가 더 커졌다면 좀 더 키워야 되는 거예요.
그렇지. 그러니까 D 값이 300을 멜팅할 300 이거 전기로는 50인데 그것보다 더 커지면 그 R을 줄이기 위해서 뭐를 키워야 되든지 PCD를 줄이든지 뭐 이래야 된다는 얘기냐는지.
그렇죠.
오케이. understand?
미체
지금 보이네.
radiation index is not the heat flux, right? Heat flux,
Yes, it's comparable.
Same one?
Yeah, same.
almost same, but the unit is different. Now I can see the unit
Okay, but it's comparable. Yeah.
comparable.
Because the heat flux is kilowatt per surface unit. Yeah?
Yes.
그럼 오늘 전기로 보이네. 다이어트 직접 구하는 거 보였네.
블루 그 스크린 고민하고 있어요.
제가 의외로 쉽다니까.
So actually normally which one is more strong between the surface of base and arc?
The arc.
Arc is more strong.
지금 저 멜팅 할 때 그 리액턴스 인덱스가
You
300을 넘지 말라는 거잖아요, 그지?
You just
인덱스. 그렇지, 인덱스.
you just imagine this surface of the bath, yeah, radiating with a temperature of let's say 16 degrees C, yeah, and this arc length radiating with 20,000 degrees C,
Yes.
yeah, and radiation is proportional to temperature times 4.
Yes.
What is the strongest you mean? The arc.
타임.
Yeah.
So in that case, how
Look,
I
the arc is able to make the scrap along the wall here.
yes.
And if you have, for example, in a COS or in a Consteel, the bath is not able to make the scrap staying there.
No.
Yeah.
But normally when the arcing is working, the scrap is located in the surrounding area,
Yeah.
right? So arc cannot, the radiation cannot transfer to the wall of WCP.
Yes.
Yes.
Yeah.
So how strong is it in that case?
It's so strong that people decided to abandon the refractory wall to go for the water cool.
Yes. That's why I want to know how strong. I mean, if you tell me the value about the radiation index from arc.
But you can calculate the decay.
Yes.
I don't know, but it's easy to calculate. So this is the arc, and this is the bottom. You can estimate
아까 길이 구하는
Yes,
거 있잖아.
nowadays to 400 millimeter. Yeah,
Yes.
to have the solid angle.
Yes.
And then the temperature here is 20,000 degree K.
Yes.
Yeah, and the radiation.
Then I can use the Stevan Boltzmann. Yes. And that's enough. Okay, I will try.
That's right. For tomorrow morning.
tomorrow morning test. 볼주가 상수예요? 저기
우체 목화부터 내가 지금 레디에이션
하도 줘가지고 오래돼서 있잖아. 지금 그게 다 기억이 안 난다.
저 이제도 안 하는데 그거.
아 너무 오래됐어.
껐어?
Okay, so
계산하는 값이 엄청 크게 나와.
we have the active power radiation index. This is for melting, this is for refining. The difference between these two is the F we take here and the F if we take F melt, and here we take the F ref. Yeah? If we are here, we have the F melt, and here the F ref. Okay? So, and 15. Well, so the out voltage we have here. No wait. So what's the difference between these two? Yeah. Okay, so in the calculation sheet, so in the calculation sheet, I have a solver. Because here I define the megawatt melting I want. Here, this is the megawatt melting. So I make here the difference from this value to the megawatt melting, here for refining. And the solver will try to put this value to 0 under constraints.
Other constraint?
Constraints.
Constraints.
Constraints. Yeah? Which means under condition. Okay. Oops. It's not loaded. Yes. So this was the last one, for example. And this is for refining phase. So N25, you see N25 means the refractory index. I try to get the minimum of it. Yeah? By changing these H30 and H32. H30, H32. Yeah? That means the MVA and the voltage. This is my variables. And the conditions are, I need to have MVA lower than 160. This is to not to avoid to have, let's say, stupid calculations going everywhere. In fact, I show you the conditions I put. Oops. Oh. No. This is the constraint. Maximum voltage between below this value. The stability has to be below 1.33 for melting and 117 for refining, which is not really a problem, but melting has to be the case. Current maximum 63. Cosinus phi minimum 0.6, 0.07, and MVA put the constraints either.
Why these as constraint? under safety?
Just to avoid that he is finding a solution out, because this is not a scientific calculation. This is optimization. So it may find a solution away from the area I want to be. So I impose him to find a solution within the area I like. And most important thing, this one has to be 0. This is this cell here has to be 0. Yeah? Okay, this is the 2010 solver, so he has a different possibility. Yeah, and the one which is working well for this kind of calculation is the non-linear. Okay, this is the way this sheet is calculated. After all, it's just, let's say, in fact, what you see here is to show this diagram. Yeah? Where for melting and refining, I have the active power curve with the points which will be selected. And on this diagram, I have the radiation index on these two curves. This is melting and refining, and this is the stability. Yeah? To see where I am situated with the stability.
The brown color is stability.
Huh?
Brown color is stability.
Red
Red.
is stability. Yeah. Yeah, on my screen is obviously red. On this one, the color are completely changed. Look, I will never select this kind of stupid color here. Yeah, it's because your beamer is changing the colors.
Okay.
Okay. Oops. Ah, yeah, I know why. Ooh.
여기서 임피던스도 계략 계산을 해주는 모양이네. 그지? 응?
임피던스는 하여튼 뭐 배치 주위에 있는 뭐 환경, 그다음 전류의 세기 변화 이런 거 다 고려를 해줘야죠.
그렇죠.
So you have the main electrical features on this part, which will be used for melting and for refining. Yeah. So the important part is the stability, refractory index, active power, and current, of course. Yeah. Then I calculate the arc length as well. Yeah. Arc length is the arc voltage. Arc voltage, yeah, minus 40, because you have 30 volts voltage drop at the plus side and 10 volts voltage drop on the minus side. And it's considered 1 volt per centimeter per millimeter, yeah, 10 volts per millimeter. So 1 volt per millimeter and 10 volts per centimeter. So as a result of the calculation and optimization, you have the MVA of the transformer and the tap voltage. Okay, this sheet is mainly not to design the transformer, because to design the transformer I'm using the Professor Tim's software, because this one is just to fix the working condition, because in the thermal balance I have to use the current to calculate the ohm losses. Yeah. But it gives indication what should be the tap voltage area range. Yeah? Of course, the transformer will be, let's say, what will be specified to the customer will be oversized compared to what is calculated here. Yeah? And the transformer taps will be adapted to what the transformer supplier is able to supply.
지금 트랜스포머 제작사하고 지금 저게 뭐가 관계된 거지?
제작사항이라면?
트랜스포머 자체가 프라이머리와 세컨드리 사이에 그 콜의 턴 횟수에 따라 이렇게 비율이 정해지기 때문에 정확히 뭐 앞단은 정해졌지 않습니까? 뭐 210kV 뭐 이렇게 그 뒷단은 턴 수에 따라 턴 수에 따라 정해지기 때문에 정확히 절감이 안 된다는 거죠. 약간 변동이 될 수 있다는 거죠.
아, 이게 MBA가?
아니요. 세컨드리.
세컨드리 주면은
어차피 기준이 다 정해져 있으니까.
약간 정확히 저걸 못 맞출 약간 거의 다 뭐 맞출 수 있겠지만 그렇지 않아요. 1V, 2V 차이로 이렇게 정확히 못 맞추죠.
오케이.
Well, you have to know that sometimes you make mistakes. Huh? For example, I remove the reactor. Yeah? Then you get a warning. Yeah? Because you get here 150 and 1. Okay?
The K is under the 1.3.
Again, not enough. Still not enough. Done.
Okay.
Of course, this as well is assumed furnace impedance and resistance. Yeah, but according to, let's say, what we know, I mean, this is even a little bit high, but it's a mixture of everything. I made several tests, so it's not really typical from this furnace of 150 ton. So, but it's coming by experience. Yeah? But this is typically the values the impedance calculation can provide.
저는 뭐 어디서 할 수 있나?
임피던스 캘큘레이션 거기에서 다 되는데 그걸 우리가 쓰면 너무 그 나온 거하고 지금 너무 재밌죠.
그게 없으면 그게 지금
지금 만약에 하이크런트 시스템 자체에 임피던스하고 이게 딱 정의가 됐잖아. 그러면 좀 만들 수 있을까?
그
툴이 있대. 임피던스 계산한 툴이 있다 하더라고요. 오전에 봤거든요, 우리가요.
그걸 별도로 사야 되는데 그걸 하려면 우리가 암하고 이거 디자인 다 할 수 있어야 돼. 암하고 하이클러드 그 케이블 있잖아. 그걸 다 우리가 선정을 할 수 있고 세컨드리 부수박까지 다 해야 그 다음에 임피던스 계산할 수 있는 거잖아.
그렇죠.
그러니까 그걸 먼저 배우고 임피던스 계산학법을 사서 운영을 하면 되는 거지.
Okay, so otherwise, so we have seen the arc length. The arc current is the this one here, which is defined by the F20. This is the MVA, yeah, divided by the voltage for 3. Yeah? The short circuit current, that means we put the electrode in contact, so we just have the impedance of the furnace. Yeah? The power in short circuit, so easy. The key factor is the this one here, which is defined by the formula we have seen initially in the previous sheet. Yeah. Secondary voltage is given by the impedance calculation either. Yeah. So this is the root 3, cosinus 3 refractory index, impedance. This is the voltage divided by the current, and this is the arc resistance, which is the arc voltage divided by the current. And this is the secondary NDA. So this is the results of the solver, but we have it here as well. Oops. We have it here as well. All conditions are fulfilled. In fact, it's just the repetition of the condition I have in the solver. So we have seen input data, analysis, material balance, electrical power. So now we go to the thermal balance. So thermal balance nowadays is not much to adjust, because everything has been prepared in the other sheets. The only thing, in case we have a DC, of course, you can forget all this stuff here. Yeah? In case of DC, you just define the power you need and the current you accept. Yeah? Because in this formula, you don't take this one, you take 0. Arc length, if you have B9, this is 1. So you take this formula in this case. Yeah? Same for the, because you have cosinus 3 equal 1 for the DC furnace. Yeah? So it's easier. If I put 2 here, oh. Yeah. I'm using this value. 2 is DC. Oops. Okay. So this is the megawatts I have defined on the input data sheet, and for safety I take let's say harmonic coefficient, because I know that during melting the power is not achieving the 95 megawatts, it's slightly increasing, so depending on the kind of process. But for the cost, for example, I start on the hot hill, so I get very rapidly to the maximum power. But for boring phase and start melting of the conventional furnace, it would be 95 or something like that. So this is the repetition of the burners and cojets. This is the repetition of the scrap. So this is injection by lances and cojets. Here I have a carbon injection. So in the consumption I calculate this time, so you can adjust the time you are injecting carbon during melting here. Yeah. Because you may start carbon injection earlier, but for refining it's considered that the carbon injection is running all the time.
All the time.
All the time. So with the furnace diameter and panel height, I am able to calculate the panel area. F5, this is the furnace diameter. So it's P time diameter plus 2 times D6. D6 is the OBT. But I don't have OBT. Yeah.
Where's the OBT?
No, because Fuchs. Getting tired.
Tired?
This is something you will not use anyway, but who knows? So imagine you have a furnace from the top with a transformer house and the high current system and the cables, and then you have the electrode columns here and electrode arms. Yeah, and here you have your furnace. And you want to, let's say, scrap density has decreased, or you want to tap more. But you cannot increase so far in the diameter itself. The best would be to have something like that. Yeah? But you cannot, because then it's collision with the existing equipment. So you don't do this, but you extend, you extend a little bit, but here you insert a straight panel. And then you go round again. And then you have straight panel. Yeah? So instead of having something wrong, you have like something like that. Yeah? And this is this extension. Yeah? So we say oval.
Oval.
So it's not EBT, it's OBT. Oval bottom tapping. Yeah? Fuchs idea. But it's in case of revamping, yeah? So that's the meaning. And the dimension put in the model is the length of this straight panel. It's patented. See, this is this dimension here. It was popular in the 90s, this OBT. So the roof surface, which is the roof itself minus the roof centerpiece, and I have a small formula to calculate the roof centerpiece itself. So in case you have a DC or AC, it's different. So you will see this in detail if you need. And from the surface, I calculate the water requirement. So this was the formula of Mr. Hill. I didn't invent this formula.
What's the AR error round?
This is the yes, this is round. Yeah, I mean to have let's say something without here a figure and comma and other stuff.
소수를 가지고 가면 되지.
143수로 그냥 넣었네. Mass below one?
Yeah.
그냥 원 컬러. 위에 60.
So we have more. You see, we have more water on the roof.
Yes.
Yeah.
What's the plus trimming? Behind the part.
This Mr. Plus. Mr. Elo is Mr. Plus.
Mr. Plus.
Mr. Let's say belt and suspensors.
Let me see. Below one color lower.
Yeah, elbow. This is nothing
18. 118.
without plus. But sometimes I know that Elo went even higher than 160. He went even to 2,230, something like that.
Isn't it heat flux?
Eh?
Isn't it heat flux 160 or 180?
No. No, this is really water cubic meter. This is cubic meter per square meter.
The result is water.
No, this is cubic meter per square meter. Because you take the surface, you take square meter
Yes.
time a coefficient where you get cubic meter per hour.
Okay, I understand what you mean.
Yeah.
Okay.
So I mean the 160 is cubic meter per minute and square meter.
왜?
속도 아닌가? 속도가
어느
속도 걔는 많이가 저기야.
무장 시간.
곱해갖고 한 미터 per 세크나.
It's meter per minute something like that.
어느 거?
160
가능하네.
60이 뭐 시간
B27에 표면적에다가 B27에다가 160 곱한 거도 있고 180 곱한 거도 있고 140 곱한 거도 있는데
다 틀리잖아.
네.
판넬, 루프, 엘보 그게 다 틀리잖아.
아, 그러니까 저거는 다른 거 구해서 루베당 아니 면적당 몇 루베가 그런다 이런 개념이 있거든.
그 속도가 또 휘 플러스하고 또 관계되고 비례하고 관계되고.
아, 그러니까 그거를 나름대로 정해놓은
그게 있는 것 같아 갖고 내가
그러니까.
그러는데
그걸 뭐
그냥
6에서 7루베 뭐 이렇게 톤당 나누면
아니 숫자인데.
그러니까
Nowadays with the high shell, they have upper shell and upper part and lower part, and they are using different speeds. Yeah.
yes.
In
Yeah.
the lower part, they are using higher speed than for the lower upper part.
And also we need to include one more, the panels, steel panel, copper panel. Actually that is also different values.
No, not
Yes.
necessary.
No?
No, because Fuchs is providing combi panels.
Combi panel. What is combi panel?
믹스 마테리얼.
Yeah, because you weld copper and steel.
Yes.
So the lower part you have two layers of copper pipes, and
Yes.
above is steel.
Yes. That's why I'm asking you.
But it's the same speed because it's on the same circuit.
But some environment we only use the copper or steel panel. So in that case, we want to calculate according to this condition. So we want to apply the case.
You get everything from Mr. Eller. He is the specialist, yeah.
So then, what about if Mr. Iller suggests some things, we want to change that part a little bit?
This one is just for thermal balance purposes,
Yes.
but no problem to change.
예를 들면 그 사람은 도움은 물어보죠.
아니 그러니까 카파의 경우는 저걸 조정하는 게 아니고
네.
카파의 그 다이아미터 있잖아.
네.
그걸 작게 뚫는다고. 그래서 유속이 빨라지게 만드는 거야. 그러니까 우리가 생각할 때 유속을 컨트롤한다고 생각을 하는데 그렇게 컨트롤하는 게 아니고 카파도 구멍을 작게 뚫는다고. 그래서 뒤에서 여기서 그래서 그 전기로의 패널에 이제 그 유화 불의 압력을 5바 이상 유지해달라, 6바 이상 유지해달라는 유가 그런 거란 말이에요. 여기서 압이 일정하게 계속 주면 작은 데서 그 양이 빠지려면 유속이 빨라져야 되잖아. 그렇게 해서 만든다고 카파는. 그런 게 됩니다. 자체가.
총체적인 건 똑같겠다. 진짜.
그래.
오케이.
Alright?
Yes.
So then, what I fix here, I mean, what I have to decide is the water delta T for meltdown and refine, roof and panels. And in fact, I check here more or less the heat flux. Yeah.
Is that delta T?
델타 T.
Yeah. Water difference, yeah, in temperature, inlet, outlet.
Why the value is so small? Normally, that should
Yeah,
be-
because I make trials and it's
Okay.
yeah, it's not a real value. So, but in fact, what I've seen that the tendency is to have, let's say, slack coating on the panels, and the heat losses in the water is rather limited. The good range right now is in the range of 40 kilowatt hours per ton in the panels. Very bad furnaces are running with 80. Very bad furnaces. Yeah. Good furnaces. I remember even 35 is a good furnace.
어차피 저거는 우리가 또 하나하나 뜯어보고 두 번째 할 때 정의를 저걸 가지고 논문 쓰듯이 있잖아. 쭉 쓴 다음에 그거를 서로 세미나를 해가지고 파악을 하고 그 다음에 이제 지금 지리서를 만들어서 한번 해야 이해가 될 것 같아. 지금 이제 어떻게 쓰는 건지 하고 어떤 게 들어있는 건지 그 다음에 여기서 일부 프로그램에서 계산해서 가져온 값 있잖아. 그것까지 같이 받아야지 지금 완벽해지잖아. 그치? 그것까지 같이 받아서 계약을 해야 된다. Okay, keep going.
Yeah. So we come to the off-gas calculation. So the volume is defined below, yeah? You will see. So I take the temperature and the post-combustion rate, and I determine the megawatts. Yeah.
How can you get the post-conversion ratio
Experience.
experience?
And I cross-check because I have the off-gas calculation here. So I consider all the openings. So the slack door, the electrode pot diameter, the roof cap. So these are the openings.
Yes.
And I define the under pressure on the roof here in millimeter in water column. So I have the air ingress in the electrode port. So this is the Bernoulli formula. Everybody knows the Bernoulli formula.
we will study the formula
All right.
after that.
So then you have the volume of CO created by the decarburization, either the forming cycle or the decarburization itself. Here you have no carbon injection, so nothing. And this is the decarburization during melting. So in kilograms of carbon, I mean percentage of carbon times the capacity, and converted into CO. And divided by melt time times 60 to have it in cubic meter per hour.
Yes.
And this is the flames of the burners. And of course cojets.
저희가 필요하다면 찾는 이것들이 다 계산해서 그지?
네, 아까 저희도 뭐다 루트 EGH 들어가고 다 그런 거 들어갔네요, 보니까.
그러니까 이제 좀 어차피 이게 이제 주로 쓰는 데이터들이니까 우리 연구를 한번 또 설명해 보자고.
그건 좀 팩터 있잖아요. 포스트 컨버전 레이트가 0.8이고
그건 경험치라니까.
그 경험치인데 그게 그 저번에 메터리얼처럼 막 이것저것 다 해보고 용량별로 이렇게 쭉 뭐 이렇게
아니 그런 건 아니고 싸워보면 내가 나중에 따로 그 해보면은 그 얼마를 풀었을 때 어떻게 다 효율이 얼마든지 이런 것들이 경험치들이 다 그 논문이라든지 제사들을 오케이.
So the volume is the total amount.
얼마 안 되지?
Approximately the total amount, yeah, because you have the addition of all air ingress. I mean nitrogen, here is nitrogen,
Yes.
plus the oxygen,
Yes.
but the remaining oxygen, because you remember at this location I have the air efficiency,
Yes.
okay? So I consider 50% is gone. All right? So plus the others here, and don't forget that the water is also vaporized. The water from the scrap.
Yes.
Yeah? So I have to convert the weight into volume. This is the meaning of these coefficients. Okay? Here, so we have the same formula and forming slide. This is the kilograms converted as well again into volume. And I have kilograms per minute, so I have to convert it to cubic meter per hour. And the total amount, this is the total, because the water is gone, and
47,800이면 먹는다고
I will consider the air ingress.
엄청 작아요, 지금.
되게 좋지.
저게 맞아요, 근데 내가 생각해도 맞는 것 같아.
다른 데 실제로 크잖아.
Well, so here I cross-check the post-combustion rate, because I have the total carbon to be, let's say, going into the off-gas in this cell, which is the total carbon. Carb is the total carbon. If you look where is carb, carb is the total carbon. Yeah. So minus the carbon remaining at the end of melting, which is calculated here, carb melt. We will see later how it's calculated. It's rather complicated. Yeah, minus the injected carbon during refining phase. Yeah, so this is the carbon which should go out. Plus we add the some carbon coming from the burners, because we have methane. H39. This is the burners,
Yes.
yeah. And H106, this is the electrode. H106, this is the electrode, total electrode consumption. Yeah, this one here. Related to the power on time proportion of this for the period of melting time. Because the 122, the 1.22 is kilograms for the complete tap to tap. Yeah? The 1.22 kilograms per ton of electrode. This is the total consumption for the whole tap to tap. But I'm considering the carbon, which is, let's say, to be going to the off gas during the power on time of the melting phase. Yeah. So that gives me the oxygen I have. So I have the air ingress plus C57. This is the oxygen from the burners. Yeah. Oxygen for melting, because I have no, let's say, burners during refining, yeah, and the rest is the total amount of oxygen I blow during melting. This is this value, yeah. But I consider that the silicon and P2O5 will be burnt during refining phase. So, of course, I don't consider it. And H39, this is the H39. Yes, the oxygen will be, which will be anyway fixed by the CH4 of the burners. So this oxygen is not available anymore. Yeah. So now I have the oxygen available. So the post-combustion rate, you see, it's oh yeah, okay. It's given by this ratio. So I have to calculate the CO and the CO2. So this is the CO, is the carbon minus the CO2, and CO2 is given by carbon and C87. Yeah. So I take here the minimum of the, because if I have enough oxygen, of course I will burn everything into CO2. Yeah. If I have enough oxygen, this, you see, this is the minimum between the carbon converted into CO2 and the oxygen. So I take the minimum of these two volumes. Alright? And here is, this is the remaining part. So the post-combustion rate is coming from the ratio of these two values. Yeah?
또 삼아서 지금 삼아서 얘기했는데 지금부터 있는 거 아닌가 지금? EAF 할 때도 우리 120톤짜리 나올 때도 그 정도 나온 거 아니야? 다른데 2만에서 4만
딴 데는 15만 정도 나왔어. 베스트 15만.
이게 액츄라고 그래 틀렸지. 그 저기
저거
에파크 할 때 33,000 얘기했었거든. 이거 34,000이라고.
SMS는 7만 2천
7만 2천.
SMS 7만 2천.
혹시는
훅스는 안 나고 조각가 나오는 게 SMS밖에 없어요.
노말하고 그
노말.
노말.
네.
노말.
노말이었지. 그냥 액츄이지.
아 지금 노말 아닌가?
액츄이지.
일주일
그때 유니티 이제 액츄. 액츄.
저기는
온도 안 했어. 보상 안 했어.
저기는
노말 액츄이지.
노말 컨디션.
노말이지.
Normal.
네.
Yeah.
저 정도 나도 내가 지금
These are normal cubic meter,
네.
not real cubic meter. Now, at this stage, I don't have calculating the temperature yet.
15만 액츄라고 컴pen세이션 한 개 15만
그렇겠지. 아, 근데 여기 이거는 이제 this is only for the EAF gas, and not included in dilution air from other. 그러니까 그거랑 하면 또 달라질 수 오케이.
This is the boundary conditions for the degusting plant at the exit of the furnace. I told you I closed the thermal balance before the elbow.
이거 뒤에.
그러니까 포스홀에서 나오는 건 SMS밖에 없나? 저렇게.
아니요. 베스트도 나와. 표현됐지 7만 5천. L9 했잖아. L9.
오케이. 다 했어 조심.
If you look, if you have seen already furnace gas analysis, this is, in average, this is typical, yeah?
Yes.
Up to 5% CO, 8% oxygen, and 30% CO2. This is, of course, you may have peaks, yeah? Up to 30% CO, yeah, of course, yeah?
투가 많네.
But this is average value, yeah?
The nitrogen is nitrogen from the air.
Yeah,
인그레션.
yeah. Because nitrogen,
기억에 끓는 게 아니네. 시원한 산소 그런 게 아니고. 여기 그렇게 보면 되겠다.
you see, you take this flow rate times 80, and then you just multiply the time by the flow rate.
얘는 일단 백가 쪽으로 우리가
And
좀
water is
산소를
coming.
해야 되겠네.
Water is coming from the burners and the scrap.
버너 앤
And the scrap.
스크랩.
And this is the volume. In fact, you calculate the volume. In this case, here you calculate the flow rate for the nitrogen, because you know the flow rate of air ingress, and then you calculate the volume later.
You mean
By the time, but for the oxygen, you calculate first the volume, because you know the volume coming from the scrap and the volume coming from the burners.
So you mean that the H2 is what do you mean H2 from the burner? It's a condensing
No,
no.
You
natural
burn
gases.
CH4.
Yeah.
Yeah, in CH4 you have
Yeah,
4H.
that's right. Yeah. I know.
So you are creating
It's
H2O.
after reactions and
Yeah.
H2O. Okay.
지금 이 시계상은 그 포스트 컨버전 에어를 쓴다는 게
그래. 내가 기억이 안
그래서
나.
그럼 이제 에어 쓰잖아. 에어를 쓰는 거 산소를 쓰는 거.
그러면 조건에 따라 다를 수도 있겠네요.
그렇지.
그것도 보여드리는 할수 없어요.
네가 얘기해봐라. 이쪽은 산소를 따로 넣어주는 개념이 아니니까.
In case of this sheet, I think the post conversion is mainly aroused by the air filtration.
Yeah.
But in case of using oxygen to react the post conversion, the nitrogen composition should be lowered. It will be lowered, right?
What do you say?
In this this sheet, I think the
Yeah, air is done by post combustion. Yeah, okay.
I think the other case using the mainly oxygen to react post combustion.
What kind of post combustion with oxygen are you mentioning? The air liquid patent or what?
The air liquid or panelli.
And he want to use just oxygen instead of air.
For post combustion?
Yes.
Many attempts. What is the result? And even Air Liquide is also, let's say, telling the truth now, is that if you put the post-combustion injection nozzles in the upper shell, you just increase the electrode consumption and the carbon consumption. Of course, you increase the productivity of the furnace, right? But using more fossil energy.
That's right.
So this is the first aspect, yeah, because maybe you increase the post-combustion, but not so far, not so far. The second point is that when you put Fe in contact with CO2, above a certain temperature, CO2 is oxidizing Fe, and you create CO and FeO. Above 800 degrees. Yeah? So, in fact, you inject more oxygen, but you burn iron, and you need more carbon. Because the post-combustion, the adiabatic temperature of the flame is 2,800 degrees.
2,800.
Yeah.
그거
Fall down.
부장님한테 계산해서 비싸게 나오는 거예요. 비싸게 나오네요. 엄청 비싸게 나오는 거.
So it's
That means you take CO at 1600, oxygen at 25. You make the reaction, CO plus oxygen gives CO2. It's even not 2000, it's 3500 at this temperature. You have the resulting gas at 3500 degrees. At this temperature, CO2 is unstable in presence of iron.
So how about this?
And even CO2 is unstable in presence of graphite.
Graphite.
Yeah? So you create CO2 around the oxygen injection, and afterward the CO2 is reduced again into CO. That's why, and if you are doing the post-combustion with air, if you take CO at 1600 and air at 20 degrees C, you create a gas at 1750 or 780, something like that. 1700 degrees. And there is no risk of oxidization. At this temperature, CO2 is not reduced by iron.
아까 2002년 사진 또래요.
The air penetration can be occurred at the slug door and the spiral hole in the slug door.
쇼가 다시 내려가는 게.
How much portion
해야
is
들어가고
what portion is more?
그러니까 그때는 MP가 CO 쪽으로 갖춰있다는 얘기는.
Slug door.
Slug door.
Yeah.
오케이, 이 정도 하자.
네.
오케이.
I don't say that we have to favorize the air ingress in the furnace, eh? I don't say that it's air ingress is good for the process.
Air increase?
Ingress. I
Yeah,
don't say. It's not because
좋다고 얘기는 안 한다 이거죠.
I compare the post-combustion with pure oxygen and post-combustion with air. It's not a matter to say that I am in favor of air ingress in the furnace. Furnace type is better than furnace with a lot of holes. Yeah. Yeah.
Of course. So I think.
But that explains why some PTI burners with air gas was so successful.
Mm.
Damn expensive, but very successful.
PCI.
PTI.
What is it?
What is that used for air together?
Yeah. It was oxygen, air, and gas. But
Yeah. So
it's an American company.
굳이 왜 안 돼? 그냥 에어 밖에 팬 달아가지고 이렇게 불어넣어도 돼. 이렇게. 그러면 난 so our main target is also if possible we have to keep the airtight. Yeah, on the inside of EAF, and we blow in the atmosphere air, yeah, using some lenses or because it is controlled by us. Yeah, so I think it is better.
Yeah, sure. But the first converters, the Bessemer converters, they were using air to let's say make decarburization of the hot metal. Not oxygen. Oxygen came in the early 20th century.
So I think why I have a mind to use the oxygen for the post combustions, we can blow out. It's not the motor stills. We only the small amount of the oxygens, yeah, through the runner, and the oxygen can be react in the upper side because of the backfilter suctions. Yeah? So they make some more high-speed combustions, post-combustions. It is one of my study points.
But I mean, these post-combustion nozzles were invented in 92,
Maybe.
or 91 or 92, and since then I made a lot of trials in several. I mean, I've seen several furnaces using this, and finally everybody has removed these post-combustion nozzles.
Yeah, I think when we use the oxygens and then the consumption of the electrode increased.
Yeah, but people preferred to increase the primary oxygen injection instead of the post-combustion. So they have removed the post-combustion nozzles and installed more supersonic lenses. This is more efficient.
Yeah, supersonic lens is more efficient.
Yeah.
I think so.
Because at this high temperature, you have to create CO, otherwise you burn iron and you lose yield.
Yeah.
And what people are selling is billet. That means they need iron to do the billet. And anyway,
less oxygen means that we can increase
1 kilograms of carbon costs less money than 1 kilogram of iron.
So yeah, I also confirmed that less consumption of the oxygens can make an increase of the yield of scraps. It's in Korea, in Japan, the yield of the scrap is 93% to 94% of it. So they reduce the oxygens.
Yeah. No, they control the oxygen.
Yeah, that's right.
They control.
Not
Not
the
reduce.
total consumption is low. Very low. That's right. Okay.
우리 지금 시간이 모자란 편이에요? 아니면 시간이 안
모자라다. 에어프도 해줍니다. 일단 가보자. 좀 이따 다시 내일 질의사항을 미리 얘기해서
오늘 봐야 돼.
일단 끝나고 정리해서 한 번 더 있으니까.
시간이 안 모자라면 좀
아니 미리 저녁에 민간장이가 다 모여서 얘기를 해. 하고 나서 그 다음에 내일 질문 날짜를 다시 하라고. 어떤 질문인지를 지금 모르잖아, 그지? 저녁에 또 끝나고 나서 같이 물어볼 거 있으면 따로 물어보고 내일 질문할 게 있으면 내일 거기서 질문하자고. 질문 너무 길게 하면 진행이 더뎌질 수 있습니다.
Okay, so let's, because before we start to to discuss about a tough topic. Let's go through the electrode consumption, which is not so complicated. So here, it's the matter to calculate the length of the electrodes, especially the hot electrode. So in fact, we take the roof height plus the panel height, the refractory height, and the bath depth. Yeah. So
The tip, that's it. Tip is
calculated length. You see, this is the calculated length. So this is H5. This is the panel height plus the refractory height, because you have, let's say, you have the panel, then the refractory, and then the bath. Okay. And I removed 0.4 for the electrode length, but I could have taken this value here. Yeah? But it doesn't vary so much. So this is the calculated length, and afterward this is the Bowman model. Yeah. So I have to adjust. You see this parameter to get the right stuff. So, side oxidization is given by this huge formula, where I consider, in case of DRI, an improvement of the grams per kilowatt hour. Typically, it's 5 kilograms per ton in case, no, 5 kilograms per kilowatt hour in case of let's say, without DRI, and less with DRI. And the tip consumption.
tip consumption.
The tip. You have two consumptions. One is the side consumption, and one is the tip consumption. Side consumption is independent from the current.
Current,
Yeah. Side consumption is just depending on the tap to tap, you see, and or oxygen consumption, I guess, as well. C101, C101. Electrode diameter. So it's the time. So this is the waiting time. So it could be power on. This is the power on. And this is the surface of the electrode. Time the length.
Time?
Length.
Time length?
This is the total, let's say, area. The side surface.
Side surface.
And this is productivity. So the higher is the productivity, the lower is the side consumption. Yeah? So, and then you have the effect of the current here. So this is so this is this coefficient, yeah? The famous coefficient. By the electrode diameter. This is the at this power. This is a complicated formula from Mr. Bowman. Again, the same Mr. Bowman from the refractory index. So you find this formula on any books, yeah?
Bowman.
Yeah. So this is the total without spray cooling, and with spray cooling. With spray cooling, tip consumption doesn't change, but side consumption is just 50%. Yeah?
Because of the spray cooling, the the consumption is increased. You mean?
Decreased.
I don't know.
Yeah. You come from 0.7 down to 0.35. Because you have just half the length of the electrode, which is red. The rest is black. but tip consumption remains the same.
우리 그까지 닿기 전에 다 충분했습니다.
아 근데 이제 저게 아직 학술적으로 약간 논란이 되고 있거든. 근데 물을 양에 따라서 뿌리는 데 따라서 저게 오히려 덕이 될 수도 있고 손이 될 수도 있고 뭐 이런 게 있거든. 오케이.
Yeah. So this time is a big value. You see as well here. So it's done by the goal seek function either. Yeah. In fact, I fix the enthalpy. This is the enthalpy of the metal, the enthalpy of the slag. This is fixed value, but this is variable value because a lot of heat losses are, let's say, time proportional. Because you have off gas in cubic meter per hour and the water in cubic meter per hour as well. Yeah. So a lot of heat losses are proportional to the time. All right. So this is a fixed value also because the burners are not efficient all the time. Exothermic reactions, this is depending as well on the time because this carbon injection is time proportional. This is a fixed value, and energy, I mean electrical energy, is also proportional to the time. So you have a lot of things which are proportional to the time, and I let the iterations to calculate the time to balance these two figures. Yeah?
Yeah, I have to balance the two figures.
Here I have the difference in the middle. I have the difference. I have in the macros balance EAF. So I just check first that the material balance is finished. Yeah? Otherwise, I do the material balance again. So this is for melting. You see, delta M, goal 60, changing cell melt time. This is delta M, and this is melt time. Yeah, very easy. So I do the same for refining. Then I get the total power on time and power of time. This is the addition of these two balls.
이거는 한번 전체 다시 분석을 해보고 다시 한번 더 받아서 확정을 하는 게 더 나을 것 같은데.
그렇죠. 이거 지금 이거 갑자기 다 천천히 뜯어보면 그게 뭐 상수 외에는 별로 아니고.
그래서 일단 내가 봤을 때는 이 부분을 가지고 이제 각 파트를 쭉쭉 나눠서 내가 줄 테니까, 그지?
그게 숙제.
아니 근데 어차피 내년에 너무 써야 되니까, 그지? 그거를 책을 쓴다 생각을 하고 이제 만들어서 그걸 이제 가지고 다른 사람들도 전파 교육을 할 수 있게끔 그렇게 하자는 거지.
재밌을까?
책 쓰는 사람보다는 다 이야기 좀 어려워. 그래서 참고서를 여러 개 보는 거잖아. 예. 그러니까 그렇게 자기가 그런 저자가 된다 생각하고 가면서 지리 리스트라든지 좀 애매한 거, 특히 상수 들어가 있는 것들, 그다음 매크로에서 나오는 것들에 대한 거를 좀 파악을 해야 되겠지. 그렇게 하자. How about break time?
눈이 아파. 눈이 아파. I feel my
Especially because first temperature is rather high and you are passive. So I mean you get tired and tired.
And the Excel formula is very difficult to understand. Excel formula is very difficult to understand.
This is very easy, yeah?
Easy? Oh.
This one is easy. D51 plus D60.
Very good. Very good.